Hello everyone. In this video we will do an example of finding arc length of a curve defined by a function. Well, remember that the arc length of such a curve is given by integral a to b of square root of 1 plus the derivative of the function squared then dx. Here the function is ln x. The derivative is going to be 1 over x. And well, it is a good function or a continuous function on the interval from 1 to 2. Okay, so this example is one of the best examples to review all the techniques that we had studied so far, at least the way I'm doing it here. So we go from 1 to 2 root of 1 plus 1 over x squared dx. Okay, this will give us integral 1 to 2 of 1 plus x squared over square root of x squared, which is absolute value of x, but since the interval is positive from 1 to 2, so just x itself comes out. Okay. Now you look at this integral. Okay, we have a rational function root 1 plus x squared, and we know that we can evaluate such an integral by the trig substitution. X equal to tan theta, which will give us dx is equal to secant squared theta d theta. Okay, so I write this one. So this will be 1 plus tan squared theta over, in the denominator there is a tan theta, and then this is secant squared theta d theta. What will happen to the intervals? So the limits of the integral when x is equal to 1, tan theta is equal to 1. That means that theta is going to be pi over 4. If x is equal to 2, then, well, okay, what is the angle whose tan is equal to 2? I don't know. I'll just write theta is going to be tan inverse of 2. Okay, so my integral now is this guy here. Okay, let's now apply the simplifications. Pi over 4 tan inverse of 2 square root of secant squared, that is secant, absolute value of secant, but since in this interval it is positive, so we can get rid of the integral, the absolute value, and then this is what we have. Now we have a trig function to integrate. It's not one of the forms that we always have in mind. But what we can do here is that we can start with simplifying, yes? So secant cube is 1 over cosine cube theta over tan theta is sine theta over cosine theta. And as you can see, this will cancel with that. There will be 2 there. And when you multiply, this will give us 1 over sine theta cosine squared theta. Okay, so I'll write that. But then, okay, even if I write that one, so let me just write it, you notice that, okay, now this is something that we have to deal with it very carefully. And the way we have to do that is, you see, we are integrating trig functions, but there is no derivative of any of these guys here. But if I multiply the numerator and the denominator by another sine theta, this will give me the derivative of cosine up to factor of -1 in the numerator. And then I can write everything in the denominator in terms of cosine as well. So this I will do squared sine theta. And you see that now I can use the substitution. U equals to cosine theta. It will turn my du will be minus sine theta d theta, which is almost there, yes? So I can multiply minus outside, and I can write my u integral, which will be du over sine squared is 1 minus cosine squared, so this will be 1 minus u squared, and that will be u squared. Very nice. What about the limits of the integral? Okay, so if theta is pi over 4, that will imply that u, which is cosine of pi over 4, is root 2 over 2. So I have this one. I have lower limit there. How about if theta is tan inverse of 2? Can I find u, which is cosine of tan inverse of 2? Here we have to use the reference angle. So this is theta. 2 over 1 is the tan of that angle. So here will be root 5. So cosine will be 1 over hypotenuse, or adjacent over hypotenuse, which is 1 over root 5. Okay, see, cosine of pi over 4 is root 2 over 2, but we can use this format so that we have both of them in the same form, and that will give me 1 over root 2, 1 over root 5. Very nice. Now we turn our integral to a new integral. This is a rational function. And to evaluate rational function, we need to use a partial fraction decomposition. So partial fraction decomposition. I know this is getting long, but see, we are using all the techniques that we have learned so far. So I want to write 1 over 1 minus u squared times u squared as sums of partial fractions. Well, to start with, you write all these cases, u and then u squared. That's how we will get. But what you will find is that the numerator of this guy is going to be 0. I'm not going to completely apply this method here. So what you will get is going to be like this, half here and half there. Yes. So then my integral would turn to sums of half 1 minus u plus half over 1 plus u plus 1 over u squared du, go from 1 over root 2 to 1 over root 5. Okay, so now we can apply the the integrals. These are easy integrals to do. So the first one is going to give us half of negative half of, so this will be positive, ln of 1 minus u, absolute value there, plus, oh, there's a minus there, half of ln of 1 plus u, then minus 1 over u, 1 over u, but there will be another minus sign multiply from outside, this one, and that one. Yes, so that will make it positive. Okay, and then this will go from 1 over root 2 to 1 over root 5. Nice. Okay, so this way, when we do apply, well, let me just write this thing a little bit more close formula using the properties that we have. Okay. And now it's time to evaluate it at 1 over root 5, which is half of ln of 1 minus 1 over root 5 over 1 plus 1 over root 5 plus 1 over 1 over root 5. That's the first part, minus half of ln of 1 minus 1 over root 2, 1 plus 1 over root 2, plus 1 over 1 over root 2, and that is what we have. So this is half ln of, so I can multiply and then simplify. Get rid of root 5. It's going to be positive number. This is going to be root 5 minus 1, root 5 plus 1. This will be plus root 5 minus half of ln of root 2 minus 1 over root 2 plus 1. Okay. And then this will be minus root 2. Yes, now I can put all the lns together. This will give us ln of square root of, so I'm putting all the properties. So here you can do one by one and you will get root. And then this is root 5 plus 1, and then times root 2 minus 1. Okay, that will be the first term. The second term, well, there is two things there, and you just evaluate that and you find what we were looking for. So this is a long solution, but this way you basically use all the techniques that we have learned from the beginning of the course for the integration. Yes. Okay,